Hello, good morning, good afternoon, good evening, wherever you are on this beautiful earth. I want to welcome you to the webinar addressing a very hot topic in the automotive industry, safety first for autonomous vehicles. Where do we stand? What is missing? So on behalf of Axel, the chairman of the industry group, autonomous vehicles for mobility as a service, I have the pleasure to guide you through the webinar today. The idea for this industry connection group of the IEEE Standards Association is to bring together stakeholders from all over the world with representations from China, the US, Europe, to set up and to plan different events addressing hot topics and challenges in the automotive industry in the transition from the ADAS systems to automating driving systems. We have set up a program committee. You see the members here. And with that, I wanted to highlight some housekeeping rules here. So the workshop will be recorded and will be available for public access after closure. Please mute your phone when you are not speaking. If you're experiencing technical issues, please use the chat feature or message the host for troubleshooting. And to pose questions to the speakers, use the chat feature on the console anytime during the broadcast. So the idea is after every presentation, so we will have four short presentations after every presentation, to have a very short 1-2 questions for clarification mainly, and then depending on where we are at the end of the webinar, to have a longer question and answer session. With that, I would like to invite Jyotika from NVIDIA to talk about standards for functional safety data format for interoperability within the dependability lifecycle.
Thanks very much, Herman, and welcome everyone to this part of the presentation on IEEE P2851. My name is Jyotika Atavale. I work at NVIDIA, and I am the chair of P2851. This is the standard for functional safety data format for interoperability within the dependability lifecycle. And on the next few slides, I will talk a little bit about an overview of what we are doing in IEEE with respect to standardization in the functional safety and dependability scope, and what we are covering in P2851. So this slide here, we briefly talk about the position of IEEE versus the other standards development organizations and how the IEEE standardization activity fits within that the governing standards, which are as listed here. We have the basic standards. These are standards in case of automotive, such as the ISO 26262, the ISO 21448, the ISO 21434. And then we have what we call the generic standards. These refer to standards such as the UL 4600, the ISO TR 4804, the ISO TS 5083. And then we also have the function-specific standards, where IEEE fits in, as you can see here in the green box, is kind of overarching or trying to provide a bridge or a glue across all of these standards. And I wanted to mention that up front here, just to clarify the scope as to the work that we're doing in IEEE P2851 does not intend to replace or change anything within each one of those basic, generic, or specific standards. But is to provide implementation guidance, support interoperability across the domains, across the levels, and across different technologies, covering those standardization gaps and addressing overarching aspects. So here we talk a little bit about the problem statement and what we are trying to address with respect to the IEEE P2851. The problem statement or the landscape that we saw there was an issue was the lack of a consistent set of methodologies, description languages, data models, or data formats to facilitate the data exchange for safety analysis and verification data across the supply chain or across domains. Here we are referring to topics that apply to across the levels, so across IP, SOC, system, and item, topics such as exchanging or integrating data from FMEDA, base failure rate, vulnerability factor analysis, etc. And due to the lack of consistent or common data formats or methods or data models, companies are struggling with many different types of or custom solutions to these methodologies and description languages, investing valuable time to reconsolidate, compare, and integrate and combine that data. As a result of this, we identified that there was an urgent need for a solution such that we could provide this consistent data exchange format to accelerate the safety engineering process while reducing risks and costs. And that's when IEEE P2851 was kicked off with an objective to deliver this consistency. The landscape, as we will define it and as included here in the presentation, defines those interoperable problem statements or needs, as we call them, for each activity, where we will need to address this issue of providing that consistency in terms of description language, data model, database, and methodology. The ultimate goal of P2851 is to provide structures and directions to facilitate that seamless exchange of information between activities the same or different levels of abstraction. So a little bit about who we are and who participates in our working group. So the IEEE P2851 has about 30 or so companies that are currently participating. These include representation from entities that are either EDA vendors, that are tool vendors. There's IP or IC providers. There's tier ones and OEMs. So a mix of all of these different entities across the value chain that participate in our working group, and about more than 70 active individuals participating. In terms of the working group officers, besides myself, there is Nir Maur, who is the vice chair, and Merav Nitsan from Synopsys, who serves as secretary. So a little bit about the position of P2851 again with respect to the other standards, and we covered a little bit about this on one of the previous slides. But here we see the domain-specific standards. So we have the ISO 26262, for example, the ISO 21448, and the UL 4600 for automotive. The IEC 61508 and the ISO 13849 for machinery, and then for avionics, we have the DO standards, the DO 254 and the DO 178C. These are the mainstream governing standards for each of the application domains. And the scope or the objective of P2851 is to provide the connection or serve as the glue between these standards such that we could exchange data across these different application domains. But not just that, we're also looking within each domain and looking at the different levels within the domain to serve the to address the objective of providing interoperability across IP, SOC, system, and item. And then also looking at how we can provide that interoperability between functional safety and each of the dependability or dependable technologies such as cybersecurity, reliability, real-time availability, maintainability, etc. So that's kind of to explain the positioning and not intending to change any of the existing requirements, but to help facilitate the data exchange across those different aspects. And here's another picture just showing that view where we're showing how P2851 would connect each of these different standards across the domains. Our first objective is to release a domain agnostic standard, which is our first revision of the base standard, which will provide the life cycle for dependability and will present the domain agnostic view, including within each one of the phases in that dependability life cycle, the topics or the activities where interoperability is critical and would need to be considered. And so last year, the working group in June published a white paper, and in this white paper, we introduced the notion of a dependability life cycle, and we also talked about how the P2851 dependability life cycle leverages the V model. So what you see here on the left is a snippet from that white paper where we talk about an example as shown here on how we need to look at all of the different requirements from each of these dependable technologies in a holistic way, such that we can consider the implications of each of those dependability attributes to functional safety. So you're seeing here an iteration of the requirements, and this is not in any particular order, but just serves as an example to show how, in this case, initially we are looking at the functional requirements definition, which then would illustrate how the performance needs to be revealed, which in that case, from there on, we would consider how to consider the requirements for reliability, functional safety, SOTIF, security, and so on, and then iterate on, analyze such that we come up with a common set or a holistic set of requirements which would consider each one of these different technologies, and such that we can come up with a dependable architecture accordingly. So that's the view that we introduced in the white paper. We also talked about the V model as shown here. And IEEE P2851 leverages the V model. When we discuss the development strategy, the reason for that is because this best represents the connection between the design activities on the left of the V and the verification activities on the right side of the V. And so here we see each one of the levels, so the item, system, component, and part unit, which includes one or more activities, and these activities belong to one or more phases of the product development life cycle. These activities could relate to intra or interlevel interfaces, and also each activity could be linked to specific methodologies and tools that need to be executed during that phase. And so we're leveraging this as we define in the dependability lifecycle within P2851 what those specific activities are. I have an example on the upcoming slide. And for each activity where we have a gap with respect to interoperability in the context of the description language, data model, database, or method. So here's some of the needs in that white paper in the annex as well. We define a list of needs that the working group had collected over the past year. So, we kicked off in 2020, and over that year, we divided into 6 subgroups focusing on various aspects, including automotive, industrial, medical, avionics, SOTIF, and cybersecurity. And each of those subgroups looked at the topics that where we had gaps with respect to interoperability, and some examples are listed here, but the total list is over 100 or so needs that we identified, and in the first revision of our base standard that we will be releasing, those needs are mapped to specific phases within the dependability lifecycle. So here you can see some examples include safety plan, safety case, description language, assumptions of use, description language, base failure rate, description language, methodologies for ASIL decomposition, dependent failure analysis, vulnerability factor analysis, and then databases for various topics as well. P2851 within IEEE reports into a functional safety standards committee, that is an overall container related to functional safety and the connection of functional safety with other dependable technologies that's focused on architectures, methodologies, and tools addressing functional safety and other safety related aspects at different levels of abstraction, spans various application fields, including automotive, industrial, avionics, and HPC. And as we mentioned, it looks at functional safety in the context of contiguous domains. So a little bit about our upcoming roadmap. And so some of our initial deliverables were a landscape document that we published. The landscape document includes the list of needs as shown here with priority, and these are the needs that we saw an example of on the previous slide, where we would need to dive in and provide a solution in terms of how we provide the consistent methods, description languages and databases, and this would be covered in the DOT standards that P2851 will deliver. So I didn't mention, but really the structure of P2851 is a family of standards. Our base standard serves to define the life cycle. The DOT standards would serve to define the implementation of each of these needs and methods and data models. And that's also where the work that the Accelera Functional Safety Working Group is doing would feed in. So the landscape document covers a description of all of these needs in priority and has an identification card, as shown here, describing for each need the description, the problem statement, proposal, limitations, etc. Then we published the white paper that was in June last year. We defined the structure of the P2851 family of standards, partitioning into the base standard revisions and the DOT standards. We had to update our scope, so the PAR update aligned with the revised scope of P2851, which covers the dependability umbrella and the role of interoperability within that dependability scope. By the end of this year, our plan is to release the first revision of the base standard, which is the domain agnostic dependability lifecycle for P2851. So that was my last slide. And I don't see any questions, but happy to take any questions from anyone.
I see. Thank you very much, Otika, for this very good overview about the ongoing work in the IEEE P2851. I see one question related to the standards you mentioned. And the question is about, shouldn't also standards from the railway community be acknowledged?
Yeah, that's a great question. So in fact, I think it is important to consider the railway standards as well, such as the CENELEC standards. Currently, we are looking at 4 application domains, so the automotive, industrial, medical, and avionics. But certainly, the scope expansion is open, and including railways is an important aspect, an important one that we should consider for the future. So certainly we'll take that into account. Appreciate that input.
Another question is about a practical method. Where can we find these documents?
Mm-hmm. Yeah, so we do have our IEEE 2851 external website, and on that web page we have posted links to the white paper that is published externally. The standard is, the base standard is still in development, so that hasn't been released yet, but the plan is to have that published by end of this year.
Another question, will it be any guidance to put P2851 into engineering practice in this version? I'm not sure. So it's not sure what it really is about this question. So it seems so the P2851. So the first standard. What is the expectation in terms of will it be implemented? And what about the other standards to follow in the family of standards?
Mm-hmm. Yeah, it's a good question. So per the family of standard structure that we've defined, this first revision of the domain agnostic dependability lifecycle will contain the definition of the dependability lifecycle, will contain the different phases of that lifecycle as proposed, showing the linkage of functional safety with each of the dependability attributes. And within each phase, we define the list of activities that need to be considered, in which of those activities have topics that where interoperability is important. In there, we will define the problem statement and normative requirements defining where interoperability will be implemented. The implementation of each of those interoperable topics will follow in the DOT standards that will follow, and that work on that will start next year. But following this first revision, the base standard will be another revision of the life cycle where we will define the domain-specific life cycle. So the Rev 1, where we will start work later this year, will include the life cycles specific to automotive, industrial, medical, and avionics, and safety critical systems.
So I see quite some questions, and I fear we can't really cover all of them. There is one remaining, which is really 2851 specific, asking, will IEEE 2851 propose a new language or a new unified data format?
Yeah, so in the DOT standards, we will define the description languages. Our intention is to leverage the existing languages as much as possible with respect to, for example, UML, SysML, and others, rather than inventing a new language. So the implementation of what those description languages and data models will look like will follow, as I said, later. But the intention is not to introduce something new as much as possible, and to leverage the state of the art where we can.
Yeah, there are many questions. I've already said some of them are generic, so they ask for challenges or answers to challenges which are not really specific for the Jyotika's presentation. So I would rather prefer to look into that at the end of the of all presentations, so that all the speakers may have an opportunity to answer and to give their views, depending on the time we will have at the end of this webinar. With that, thank you very much, Jyotika.
Thank you so much. Thanks for the great questions and feedback. Appreciate it. Thanks, Herman. And
we go to the next presentation, which will be given by Professor Burton from Fraunhofer IKS in Munich, I understand, and it's about safety and AI for automotive systems. The floor is yours.
Okay. Thank you, Herman. Can everybody hear me fine?
Yes, I can hear you.
Okay, great. Yes. So let's start. So in this presentation, I'll give a quick overview of some of the challenges related to the introduction of artificial intelligence and specifically machine learning technologies into the automotive domain. And to do that, I'll give a very brief context. What is changing with these classes of systems we're currently developing, and why is machine learning and artificial intelligence creating even more challenges for the development of these systems. I'll give a very quick overview of some of the standardization activities which I'm personally involved in related to the ISO family of standards, and I'll wrap up with some insights into some of the areas of research that we're currently working on and some of the maybe still unanswered questions that we need to work on. So first of all, let's look at the classes of systems that we're currently developing as an industry. So IKS, the name of my institute, stands for the Institute for Cognitive Systems. What do we understand as a cognitive system? Well, this is a system that is software intensive. It's a technical system. We refer to embedded cyber-physical systems, but we call them cognitive systems because somehow they need to imitate cognitive capabilities such as perception, learning, and reasoning to fulfill very complex tasks. And I deliberately say imitate there because we try to avoid getting into a discussion as to whether these systems are truly intelligent or whether they are really making rational decisions, etc. But they need to have some understanding of their environment and choose the correct course of action. And you can see some of the types of applications we're currently working on here. If we go back to, I would say, the classic understanding of functional safety of embedded systems as we see in the automotive area, Jyotika already mentioned the ISO 26262 standard, which talks about functional safety. And safety was often determined by the absence of unreasonable risk due to hazards caused by malfunctioning behavior of the electrical systems. Malfunctioning behavior in terms of things that break or are broken. So in other words, random hardware errors or systematic errors in the hardware and software. And we see actually that is now only one very small part of the story we have to deal with when we talk about safety of such systems. So what's changing? In general, in a nutshell, we can say that the systems and their environments are becoming more complex and the level of uncertainty in these systems is increasing. So for example, let's start off with the environment. So these systems operate in a very complex, unpredictable, almost unmodelable environment where they need to somehow make sense of the world around them, complex traffic flows, the visual characteristics of pedestrians and other objects on the road, etc. And this environment is changing all the time as well and is very unpredictable. So that's one source of complexity and uncertainty. But then we try to measure this environment using a set of sensors with a very diverse set of technologies from radar, LiDAR through to camera-based systems. And as we know, these sensors also aren't perfect. So there's always a certain amount of noise involved or inaccuracies involved in the sensor technologies we use. So in other words, we're trying to capture this very complex environment with a set of noisy sensor inputs, effectively. Well, this is where, in some senses, machine learning and artificial intelligence comes to the rescue, because machine learning, in particular, as a data-based methodology, seems to be very good at making sense of very complex data. And as you can see here in the picture on the right, machine learning algorithms seem to be very good at identifying certain objects in a scene, classifying the difference between pedestrians, people on bicycles, other vehicles, and other parts of the scenery, as it were. However, the use of machine learning itself introduced another set of challenges. Machine learning algorithms themselves produce not very predictable results and introduce a set of uncertainty in their calculations themselves. And this is, on the one hand, as I say, they can help. On the other hand, they just seem to add more problems, especially for us safety engineers. So there's a certain terminology we use here to describe this problem of the impact of complexity and uncertainty. And this is called the semantic gap. And this is effectively the difference between the complexity of the system and the environment we're trying to develop a system for, and our ability to actually specify in detail exactly how this system should operate. So you can imagine the difficulty in defining the behavior and characteristics visually of every single possible pedestrian we would come across in the road. And these semantic gaps, this discrepancy between the intended functionality and that which we can specify and therefore also test, leads to effectively a set of problems in terms of determining whether or not we've completely specified our system, but also they can lead to certain technical uncertainties and problems in the implementations of the systems, which further on can lead to gaps in our ability to argue the safety of such systems, including ambiguities regarding the legal responsibilities in the operation of such systems, and going as far as what we would call moral responsibility gaps. In other words, who is at fault if the system misbehaves? So what's all this got to do with machine learning in particular? What you can see here on the right of the slide is actually an accident report from NTSB, where a prototypical vehicle running in automated driving mode collided with a pedestrian, and the safety driver was distracted at the time and therefore couldn't prevent the crash. The text is very small here because I don't have time to explain it, but what you can see here in the red is basically the accident report determined that the perception system on the vehicle kept reclassifying the object over and over. As it was getting closer to the object, it thought the object was a pedestrian, and then a bicycle, and then some other object. And each time it reset the trajectory planning, and therefore basically forgot that the object was there and had to start again. The use of machine learning here was really, you can see how a lot of these problems can occur because on the one hand, in terms of this semantic gap, we don't have an explicit definition of what a safe behavior is. It's somehow hidden in the data. At the same time, as I say, we have a very unpredictable environment. So we may train a system, train a machine learning function to be, pretty good under a certain set of conditions. Once we release that function into the wild, those set of conditions can change over time. The behavior and appearance of other objects in the environment might change due to fashion trends, new technologies, etc. Then we have the technical characteristics of the machine learning functions themselves, which we refer to as robustness and generalization, amongst other things, which means that they can be very sensitive to very small changes to the inputs. So changes to the inputs, which we as humans maybe wouldn't even recognize, could actually lead to a completely different output in the machine learning function. So it seems to be a very unstable behavior. It can work most of the time, but sometimes it can surprise us. prediction uncertainty is related to the fact that these functions typically deliver not only a result in terms of a classification of an object, for example, but also a confidence whether or not this result should be trusted or not. Unfortunately, this confidence score these algorithms provide us with are often misleading. They can often be overconfident, and we call this prediction uncertainty. So on the one hand, we have this additional information which might help us to argue safety in terms of how confident the system is at any piece of time. But do we really trust it, and what can we actually do with this information? And the last point is explainability, where due to the complexity of these functions and the millions of parameters these functions use, it's very difficult to understand exactly why a function chose to take a certain action. So in summary, what we see is for this class of technologies and this class of problems we're trying to solve, even when we're executing without malfunctions, without any software bugs, without any hardware failures, and according to the specification, an AI-enabled cognitive cyber-physical system can still be or become unsafe in the future. And this is a set of safety challenges that we're presented with, and we need to somehow address both in terms of the technologies we develop, which I have to say are still to a great extent in the research phase still, but also the standardization frameworks to actually support the introduction of these technologies. So let's look quickly at the role of standards here. I probably don't have to remind too many people in the audience why we have standards, right? They help us, amongst other things, to define a common benchmark across the industry to measure what we consider as state of the art, which in turn is also used in terms of liability law, where standards, internationally published standards, can be considered the lower bound of state of the art. They can also help us actually decide how to assess whether or not our systems have mapped certain levels of safety, and therefore they can be used to create assessment criteria against which the systems can be qualified, for example. Let's look at the topic of artificial intelligence then, or machine learning. So within Europe, there's an initiative within the European Parliament to create a new set of regulations to help regulate the use of artificial intelligence technologies. As you've noticed, I try to avoid the term artificial intelligence because I find it can be misleading, but let's forgive the European Union here and go with the flow. And they also talk about trustworthy AI. And you can see here there's a set of criteria that are defined what it means to be trustworthy as an AI function or a machine learning function. These include some criteria which are fairly, I'd say, technical, such as robustness and safety, but also other criteria which are maybe slightly more esoteric for us engineers, such as diversity, non-discrimination, but also accountability and human agency. So as a safety engineer, we're faced with a challenge here of how do we use our safety engineering techniques in terms of systematic processes, methods, and tools to collect evidence that we can argue that these maybe slightly fuzzy criteria regarding trustworthy AI are really fulfilled. So to do that, we need somehow some sort of translation. We need some translation between these very high-level trustworthiness criteria to what we can actually technically influence and measure. And from my perspective, I think this is where standards can help. It's help to create that sort of translation, to create a common level of understanding. And this is where I'll move on to some of the current standardization activities. This slide is slightly complicated, but almost by design, just to demonstrate the amount of work going on just within the ISO community on developing a family of standards for these types of technologies. What we can see here on the left-hand side of the slide are a set of generic standards for AI that are being developed, where these standards, going from the top of the slide down, have an increasing level of detail to them. So the standard 22989 defines a set of terms and definitions to be used when talking about AI. And then we have standards talking about trustworthiness criteria, which is somehow related to the last slide I showed. And then we have some more detailed technical reports that are in development, looking at specific requirements and specific performance characteristics. Then in the middle of the slide, we see our generic safety standards, such as 61508, which we would have just seen on one of Jyothika's slides. And within that generic safety family, there's also a generic safety standard or technical report being developed for the use of AI in safety standards. In the automotive industry, though, we have our own family of standards. We have our own way of talking about safety, functional safety related to 26262, as I mentioned, but also the safety of the intended functionality, which addresses some of these challenges I presented in the past. And within this context, last year, I took over the lead for a new publicly available specification, 8800, which is looking specifically at the use of AI in safety-related functions within the automotive domain. And this publicly available specification should act somehow as a translation between some of these generic standards, as well as some of the industry-specific safety standards, to explain how could we argue the safety of artificial intelligence when using it in road vehicles. In the next few slides, I'll give you a very quick insight into some of the topics we're talking about. The slides shouldn't be interpreted as this is what you should expect to be in the standard once it's released at the end of next year, but they give an insight into the sort of things we're discussing at the moment. And this slide is actually the official purpose and scope of the standard, and what you can see here is actually we're addressing the entire life cycle of the development of an AI-based function, from the definition of safety-related properties, considerations related to the data we use to train and test a function, through to architectural measures for integrating the function, as well as obviously tests and assessment properties. One of the concepts which the standard will most definitely address is this challenge of specifying the right set of safety relevant properties of the function. So here we'll be addressing the difficulty in translating functional safety requirements into a set of properties which we can directly measure and influence at the machine learning level. And this is addressing things such as the types of KPIs and metrics that are currently being used to measure the performance of AI and whether or not they're really suitable to be used in a safety critical context. At the same time as trying to develop the requirements or the technical performance parameters we need to achieve with our machine learning function, we also need to find ways of describing the input domain sufficiently. So as well as defining what a pedestrian is, we need to maybe take into account how often certain types of pedestrians occur, how often should we expect them to occur in our training data and test data, and take that into account as well. At the core of the standard, just like in many other standards, there will be an analytical approach to trying to understand what types of errors in the system and within the components could lead to safety-related failures. This is what this somewhat abstract diagram is showing here, that we have at some point a trained machine learning model which is encapsulated somehow, maybe have some pre and post conditions, processing associated with that. And errors can occur at different places within this machine learning component. And these errors are caused by different fundamental properties of machine learning and fundamental properties of the data. So one of the things the standard will be looking at is how we can actually translate some of these typical causes of problems with machine learning functions into a set of measures that we can directly apply and assess during the development. anybody who's worked on things like failure modes and effects analyses, FMEAs, FTAs, etc., will be familiar with some of these concepts, which will be expressing in the standard. Also, one of the things we'll be looking at the standard is some life cycle to show how all these activities fit together. I won't go into details with these on this slide. I think it will be available as a handout, but the key takeaway here is, in comparison to the V model we see traditionally, we need to acknowledge the inherently iterative approach to developing these types of systems. In the middle, there's like a DevOps-like approach to the iterative development of the function in terms of collecting data, training the function, testing the function, understanding its weaknesses and revisiting that, but also in terms of defining the right set of safety-related properties, introducing the function into the field, monitoring the use of the function in the field and the types of difficulties we see occurring in operations. That also needs to be wrapped up in an iterative approach as well. That was also something we'll be addressing. One thing I want to warn, though, is this is an extremely complex topic. Within this first version of the standard, we will certainly won't be able to reach the level of detail we would actually like to achieve. So the question here is, what do we do, right? Given this limited time and the need to actually make some progress here. So with this slide, basically, I've, in a slightly sort of provocative manner, sort of listed the options we have available to ourselves, right? So we can either sort of stick our head in a bucket of sand and try to argue that whenever we use machine learning or AI in automotive, it's not going to do anything safety critical, right? It's somehow there in the background helping, but it's not safety critical. We can do that, but we would have so many conservative safety barriers built around our function that we won't really be able to tap into the real potential of machine learning to actually support safety enhancing features in the vehicles. We can also wait until we've got a perfect set of safety assurance methods with proven in use tools and methods and etc. That's not going to happen anytime soon either. So what else can we do? Well, the path we'll be taking in the standardization is trying to really define at first what are the criteria for effective and convincing safety assurance arguments that need to be made, leaving quite a lot of freedom as to how those arguments are actually achieved and with which technologies they're achieved. And then as time progresses and we can develop best practice for developing these types of arguments, then we can maybe look at standardizing some of the sort of the technologies and methods and metrics that seem to sort of prove themselves. So I'd like to come to the end of my presentation now to give you an overview of really where we're going as an industry here and also in research. So I see part of my task at Fraunhofer is to try to take the magic out of AI, right? So it's certainly currently seen as some sort of voodoo child of software engineering, and we need to unwrap some of the complexity here. And that will involve applying a lot of fundamental safety engineering principles, defining what an acceptable level of safety is, defining a set of safety properties to be fulfilled, identifying what are effective methods for collecting safety evidence, and combining those in some sort of safety life cycle. But then, as we know with these types of technologies, the game is not over. Once we've developed the system, we need to continuously monitor it in the field. However, there's a lot of unanswered questions that still need to be resolved, and that's where my research work comes in. I formulated them in a slightly pithy manner here. The first is finding the right tool for the job. A many-layered convolutional neural network with millions and millions of parameters might not necessarily be the right path to go for a safety critical function. Are we sure we're using the right technologies to fulfill the needs we have, or are we just using technologies because they're currently on vogue? we'll have the problem that actually we need to have a multi-criteria optimization of lots of different parameters and goals, and that is something that will require some work because machine learning is effectively an optimization game. How do we find a global optimum whilst not by having an achievement of a minimal level of performance in certain issues? How do we reduce the uncertainty in these functions? How do we make sure that we're not going to be surprised by random errors that a human would never make? And how do we know for what type of inputs the system is more likely to make those types of mistakes? And lastly, don't leave it to chance. Is there any way we can actually understand better how these functions are forming their decisions? Can they explain to us in some way why they're reaching a decision? And can we use that information for our safety assurance activities? So as you can see, it's as a researcher, it's a very, very exciting field to be in. We're currently in a little bit of a race because these technologies are being introduced, and we need to make sure we have the standards in place and the assurance methodologies in place whilst these technologies mature. And therefore, we'll need to have a slightly more agile and dynamic approach to maybe some technologies we've used in the past. So with that, I don't know if we have time for one or two questions, but I'll be available to the end just in case we don't.
Yeah, thank you, Simon. Yeah, I think there are, at least I had in mind to pick up two questions which are related to the semantic gap. One comment is about machine learning components. Can we say that they are intrinsically unsafe? And the other one is about what about the semantic gaps for road vehicles and for railways? So
two excellent questions.
The semantic gap be, I don't know, smaller or somehow at least different on the road and due to the more or less complex environment?
So two very excellent questions. So for the first question, whether machine learning technologies are intrinsically unsafe, it really depends on how you define unsafe and how you use these technologies. What is true are that they have a set of challenges associated with them, which are very different to classical software. So one of these challenges is that they are effectively a probabilistic-based approach. So we have to understand that there will be residual errors in the calculations. Now, it could be that we can demonstrate with a certain level of probability that those residual errors don't lead to hazardous behavior of the vehicle. So we may get the answer slightly wrong, but in a safe way, or get it wrong in a way that we can somehow detect with other mechanisms. That is why partly there's the definition of what we understand as safety-related properties of the function is so difficult, where we have to invest a lot more effort because it's not just an absolute answer, the software is 100% correct. So that is a very big unanswered question. The second question I absolutely love because it's something I've been thinking very intensely about. So independent of AI and machine learning, I did some work the last few years looking at how the complexity of socio-technical systems is increasing over time and what that means for our ability to argue the safety of these systems. And my hypothesis is there is a difference in level of complexity between different systems. And there's at a number of different levels, you could argue that the task of achieving driverless train operations is inherently less complex than the task of operating a vehicle in an inner city without a driver. And that complexity can be addressed at very many different levels, from the complexity of defining risk acceptance criteria in some sort of probabilistic manner, through to the actual environment they're operating in, through to the types of assumptions you can make about the behavior of people within the environment, right? So it's illegal to trespass onto railway lines in Germany, for example, but it's not illegal to walk into the road. So that's an excellent question, and that is something that I personally am going to be looking at in the future, and how to answer that question, not only from a technical perspective, but also from a regulatory perspective and standards perspective and operations perspective as well. So thank you very much for that question.
Thank you. Thank you again, Simon, and thank you for the answers. So in the interest of time, although there are many more interesting questions triggering a discussion actually, but in the interest of time, I think we go to the next presentation, and the next presenter will be Michael Paulweber from AVL, and he will talk about ADAS and AD safety argumentation. Paul, the floor is yours.
Okay, thanks for the introduction, and I would want to thank all the previous speakers, because they did an excellent stage for what I would like to talk. Simon presented very excellent all the challenges we have. Nevertheless, we have advanced driver assistance systems which we want to bring under the market, and we are steering towards autonomous driving. The question is, how can we use all that, and how we can overcome all these challenges? We all know the V model, which more or less defines that you define all your requirements, what you would like to have, and then you gradually build your system, and on all layers you check back against these requirements, and at the end you can say you are safe. Practically, it says your design, your requirements have to be correct, so it's safety by design, and then you check that you really fulfilled what you have. The problem there is that we have so many situations with such an automated vehicle or train or airplane or whatever it is has to operate, and that it's on the one hand difficult to check if it's safe in all the situations. The even more critical problem is that, thanks God, the real critical situations in real traffic are very rare. Otherwise, you would have all the time fatal accidents, which means that just driving around won't solve the problem, because you would have to drive way too long to statistically can prove that you have covered the most important or the real relevant critical situation. So our problem is that safety by design is difficult, because a lot of the real critical situations are not known, therefore they're not specified in the requirements and cannot be solved. There's a common understanding that the only solution is that you have another safety layer, the safety by monitoring. It means that also during operation you check all the time if something happens which you did not consider during the design phase. And if something happens which gets you close to a critical situation or even brings you into a critical situation, you have to closely look back and close the backup cycle that after analyzing, collecting and analyzing, that you change at the end your requirements and create another version of your system. In most cases, it will be an updated software, and with over the air update, you can then get your system more safe. What does that mean? We really have to think about these different layers now, and if we want to do a safety recommendation, we have to work on all these different areas. When we start with safety by design, actually what that means is we want to collect engineering knowledge, which kind of problems can occur, and which state-of-the-art development methods can be applied, that you are as close as possible to requirements, which will really cover all the safety relevant situations. On the next step, then you have to check, that's common in the read process, that you have implemented everything as according to the specification, which includes also the functional safety. There you have to check what can happen if the system has internal failures, and how you cope with these situations that you do not bring the system into a really critical situation. The other version, well explained by the previous speakers, is that that's not enough. If you just consider internal failures, you have also to consider what can be happening on the outside. The outside might be that the driver in the system interferes in the wrong way with the system, because he or she does not understand what the system wants to tell him, especially in handover situations, or that your sensors don't classify certain things correctly, or don't see things for whatever reasons, and you have to check that safety typically by validation, that you can cope with this. In addition, you have another layer of problems which you have to check, that's the communication layer. It's common understanding that automated systems communicate with each other as well as with the infrastructure, and in there you have lots of possibility to interfere. That's more or less the cybersecurity level where you have to check that you are safe. A similar thing can be that you spoof your sensors, that you trick a radar sensor or a camera with this information that is by a malicious attack detects certain things wrong or classifies things wrong. And then you have to bring that into your DevOps, that you integrate the monitor, and you have to check that is working, and that also your over-the-air updates are working. If you consider all that, it's a common understanding that you cannot test just in driving around or in testing with real systems. You have to do a lot in simulation, which means that you get another layer which you have to check and test, that your simulation environment really represents in an adequate way the real systems which you want to test. If you look at it from another perspective, practically all these automated automation systems, whether it's in the mobility area of the vehicles or trucks or trains, whatever, they consist of three layers. They have a sense, perception layer, then with that understanding of the environment around you, you have a planning layer, then you have to influence your vehicle, that's the act layer. In all of these layers, you can have these three problem areas, which I explained before, which means you have to check that the functionality which is specified is really implemented correctly. You have to check safety mitigation for internal risks, and then you have to check if you have a safe handling of known and unknown situation influenced by the environment. There you can see in this matrix I have tried to collect potential approaches. If you do perception testing, you check against your requirements, then it's perception testing, and there activities going on presented by Dr. Simon before, because there's a lot of neural networks involved, will be the way. If you go to this example to the think area, then scenario-based testing is the one, because planning means how the system calculates whether it should make a break, or it should steer around on the left-hand side, on the right-hand side, or a combination. It might have to accelerate. These are all scenarios. So scenario-based testing is the way to move, and there especially this testing of the simulation models is one of the unsolved problems, because we'll come to that later. At the moment, I haven't found the standard with Apache in there. In the ACT, there's also a lot of scenario-based testing. Here we have a number of activities going on, especially from the INCAP consortia and UNCE, especially in these other functions, there you have a lot of standards out there. If you go to the middle, again, perception testing, where you introduce sensor failures, or in the sync, you have the error inflection, you see how the system reacts, cybersecurity testing, where you try to break into the system. Or in the last one, you try to figure out what are difficult environment situations, difficult weather situations, somebody is blinding you. There you check how your system can cope with that. In the sync, it's again scenario-based testing together with this in this difficult situation. And on the system level, you try to figure out how much of the already collected or monitored situations you have tested in your validation. Yeah, all of that I have covered. If you now try to see what are the standards out there, a number of the standards we already mentioned, explained in detail by the previous speakers, we can see that we have, on the one hand, standards dealing with requirement specification, other set of standards dealing with the implementation to see if everything is done correctly. Then we have standards to test the complete system prior release, and you have standards dealing with this in-field operation and the DevOps cycle. And additionally, we have this simulation trustworthiness, which I explained before. If you add these three different safety check layers, the safety design is on the left-hand side. In the middle, you have the safety by verification and validation, and on the right-hand side, you have the safety by monitoring, which we had to add. Here, I tried to summarize all of the standards I have found so far, and I try to classify them into the different areas. I won't go into all the details. I guess the slides are distributed later, and you can look at it. You will find a number of the standards which were presented in more detail before. I would like to go a little deeper in this ISO 21448 in the SOTIF, safety of the intended function, and there one entity is introduced, this operational design domain, which nothing more. It defines in which environment the system has to operate safely, and where the system has to hand back the control to the driver, whether it's in a car, the driver, or in a train, or in an airplane, as soon as it identifies that it reaches the limit. In a car, the operation design domain can be specified by the weather conditions in which it shall operate, the type of roads in which it should operate, the speed areas in which it should operate, also the countries in which it should operate. So you might have different operation design domains for different vehicles, and the design domain at the end defines what you have to test. In the design domain, you have 4 different areas which you have to handle differently. There are areas which you know and areas which you don't know. And in each of these areas, you have to identify in a known area what is a safe area and what is a known unsafe area, and you have to try to reduce the known unsafe area. And more difficult in the unknown area, so that this long tail is this very rare situations which can occur. You have also unknown safe areas, which doesn't bother you that much, but the unknown unsafe areas are the really critical ones. And the question is, what our approach is to minimize these unsafe areas that are known or unknown. So let's first take a look at the known area. In the known area, it's also a lot about monitoring. You can monitor scenarios observed on the road within your operational design domain. You can then split it into what we call scenarios, and the scenarios, for example, that you follow a car, or that you have to brake behind the car. you can then split into different scenario parameters. The scenario parameters have certain parameter density function. There are certain parameters which are more likely to occur, others which are very seldom. Then you can calculate the exposure of the different scenarios within your ODD, which are more likely, which are less likely. You can simulate and identify surrogate functions then of these different scenarios and evaluate the success of the outcome. Then you can calculate the probability and the controllability of this intelligent subset of the scenarios, that those which are more likely, that those which are very unlikely, you might not take into account. And from there, you can then calculate the injury rate, and from there you can calculate the risk in a known area, which is the exposure multiplied by severity multiplied by controllability. All of that is very well described in an IEEE paper, which I have noted out there. It describes what the procedure and method is developed by different companies and led by TNO. If you want to take a look, you can use the source information in the presentation. What does that practically mean? You drive around with normal cars and you just try to collect what you see around it, what can happen around there, and then you split it into different scenarios from different classes. So whatever you see, you're either driving without the car around you, without other pedestrians, or you have a situation where someone wants to cross the street, or you get to a roundabout, all kinds of different things. And every of these scenarios then in your ODD has a certain probability. It's described. There exists a number of different approaches how to classify them. One is from the Pegasus initiative in Germany, the other one is streetwise activity. There's others going on in the US to have this. And you also define the scenario parameters and these probability density functions of the different parameters. And in addition, you also have to collect what are the weather and road conditions for which these probability density functions occur. Because you can imagine if you drive on a sunny day on a dry road, you perform differently in the same traffic situation as when you drive in heavy snowfall on an icy road. And then this probability density function will look completely different. When you have that for the different scenarios which can happen in your ODD, then you can use the methods described before, and you have a method to calculate the residual risk, so the area in which non-safe situations can occur. But that is just for this safe area. For the unsafe area, we have to predict what can happen in addition, although it was not seen before. So it's more or less trying to look into the future. So what are the methods out there? We have found two different approaches. The one is you try to describe from your ODD definition and from the functions, from the automation functions you're implementing, you are creating an ontology. And from the ontology, you create synthetic scenarios, and then you use again the same method I described before to figure out which of these synthetically generated scenarios lead to unsafe situations, which lead to safe situations. The other possibility is that you use the information from what I have shown before, and you're now trying to create new scenarios by introducing these triggering events. What we have up to now is that I described before, and now you can add things which can happen in all of these scenarios. For example, a child crosses the street, and that can happen on a pathway. That can happen on a roundabout, that can happen on a highway, that can happen on the sunshine, in rain conditions, that can happen during taking over, and so on. In all situations, that can happen where somebody throws a ball in front of you, or a car in front of you loses some luggage from a trailer or so, or that you get blinded, and there is a long list of potential dangerous events which can occur. Here, there is a proposal from the Japanese activities going on. They have created a long list of these potential dangerous situations, which you now can combine with the information you have collected before, in a synthetic way. That you are now using the scenarios with their probabilities, with the description, and then you add these potential critical events to the scenarios, and you create a new scenario, which is most likely more difficult, most likely has a higher probability that a critical situation occurs, because these external critical events are really what when you as a driving novice on the streets where you might get into trouble. You can even extend it by adding, for example, malicious attacks, cyber attacks, or that somebody wants to prick your sensors. Or you can also add information from the functional safety, that you have a loose connector, you have a short circuit, you have battery going low, and so on. So all this can be added and can be generated to get an information about these very rare situations, because the more you combine, the less probable it will be, but nevertheless, it can occur, and you have to prove that you can handle it. That means you get a real large number of scenarios which you cannot produce on the road, because it's not easy to influence the weather, and you will not find a child which intentionally passes a car at a very narrow range. So you have to do that in simulation, and in there, now that's exactly where we need then this new standard, these new areas where we check if the simulation environment really represents or is a digital twin of the environment as well as of the system and the test we are checking. What we need is then a completely open test environment for the safety argumentation. That's one proposal to create that. First, you collect all the information of the scenarios, whether you collect them from the real world, you engineer them from your requirements, from regulatory stuff, or you generate these synthetic scenarios. You need all the models of the vehicle, the sensors, the control, the outside world, together with the statistics, the KPI, and then you generate the tests, and you can run them, especially then in a scalable simulation, somewhere in the cloud with 10,000 or 100,000 of parallel executions, and then you try to figure out where are these very unlikely situations where the system gets into trouble, and when you are using the probabilities, using the comparability, using the potential harm to the passengers as well as to the outside traffic participants, you can calculate the residual risk to see whether it's safe or not. So that's all what I wanted to present, and to more or less bring all these standards which were presented before into some potential engineering way to use it right now. Also, we know there are still a lot of standards missing, and a lot of knowledge which we gain using these procedures should be moved forward in standards like UL 46, which in my opinion is just a best practice collection, which is at the very beginning very helpful. Unfortunately, I can take maybe one or two questions.
Thank you,
then I have to
Michael.
step out because I have to go to another meeting where I have to represent the industry association, which we have our annual meetings, and we need a quorum, and I have to be there in 5 minutes from now.
Okay, thank you, Michael, and for sharing on all these ideas and this information with us. So there are some more questions, of course, but in the interest of time, I would rather go to the next presentation and then we come back to, for example, what is the role of communication, what is the role of sensors, what about the validation tool chain towards the end of this webinar. Thank you, Michael.
I have to step out now. I won't be in the end of the webinar because I have to head to the other meeting.
Okay, understood. Thank you.
Okay, thank you, and thank you for the opportunity. And yeah, we will continue to talk in the next meetings. Yeah. Thank you.
So we come to the last presentation for today. It's about engineering practice of SOTIF in China. And it's a real pleasure to welcome Qidong Zhao. Sorry for the wrong pronunciation, I suppose. From Qatar. So we are interested to hear the viewpoint of Qatar from China. The floor is yours.
Yeah, thanks a lot, Herman. Yeah, it's quite correct pronunciation. It doesn't really matter. Yeah, and thank you for the previous presenters, and also many thanks for IEEE to invite me to this to give this presentation. And my topic is about engineering practice of SOTIF in China. So first of all, I would like to have a very brief introduction about myself. And I finished my master's degree at UC Berkeley. And after that, I joined the Qatar, focusing on the risk scenario generation and the SOTIF area. Currently, I'm working as a SOTIF project manager at Qatar. And I'm responsible for SOTIF research and joint projects, and also supporting the Chinese national standard conversion of ISO 21448. Also something about Qatar. So Qatar is located in China, and we are the largest testing and certification institution in China. We also provide technical support to the standards and regulation making progress. Yeah. So let's get started. So today I'm going to talk about 5 parts, and the first part is about the background of SOTIF and what is SOTIF and why it's SOTIF important. So the full name of SOTIF is the safety of the intent and functionality. And here's a very typical SOTIF related risk scenario. On the left-hand side, it's a vehicle that crashed into a white truck when it's driving on the highway. And before the accident happened, actually the white truck was laying down on the road, and the autonomous driving vehicle had its ADAS function on. And when we review the accident, we can tell that the sensing system of the vehicle did not see the truck. Just put it simple, that the first reason is that the radar will filter out the that with very low velocity, and because in most cases there can be noise, and it's also very challenging for the camera to tell the object apart from the environment. Especially when they are in the same color, and as a consequence, the accident happened. On the right-hand side is another vehicle with its ADAS function on and did not see the roadwork and then crashed into the construction site. Typical SOTIF scenarios, usually with no electronic system failure or malfunctions, but with insufficiency of function design or technology. And this is a very brief statistics regarding the fatal accidents of autopilot from 2014 to 2017. As we can see, the trend of data, the accidents related to AD or ADAS function are increasing in recent years, and these kinds of risks cannot be systematically solved by the previous approaches. So we do need some other solutions to tackle these problems. So in the current situation of SOTIF development, both globally and in China. So regarding the different roles that OEMs and suppliers play in SOTIF, is pretty much like the division of the work in the functional safety. Since there are more than one party getting involved in this vehicle development and testing, so all different parties have their own responsibilities and interest in this SOTIF life cycle. And typically, OEMs focus on the vehicle level development and testing, and the suppliers focus on the component level and development and testing. So globally speaking, we have a lot of OEMs and suppliers that make great efforts in this area. For example, like BMW, Volvo, and for suppliers, we also have Aptiv, Bosch, et cetera. And according to our research and projects experience, we can see that we also have many OEMs and suppliers in China, which some of them are very famous in the world, like Huawei or Baidu, and also some OEMs like Chang'an or Chery. They put a lot of efforts and they invested a lot, no matter in terms of funds or engineers into this SOTIF area. And so, as we can see, it's going to be a very hot and popular area in this autonomous driving. And next, I would like to talk about the standards and regulations specifically related to SOTIF, and also including the most important reference in this area, the ISO 21448. So on the top, we can see the ISO standard working group. That is the working group for both function and safety and SOTIF. And on the top right, that is the standards in China. So we also have like a standardization working group that is trying to convert the ISO standard into a Chinese version. I think maybe just several months later or a year later, we are going to have a Chinese version SOTIF standards, which can be a bit different from the ISO 21448. Considering the special road feature and the driving condition in China. And on the other hand is the UNECE regulation. We have regulations for braking and steering system, and also for AEB or ALKS system. We have a R13 or R157, and these are more or less either related to functional safety or SOTIF. And specifically in China, we have regulatory framework that it has requirements on both functionality and SOTIF. The full name in China, we call it Production Enterprises and the Productions Market Access Management Guidance for Intelligence Connected Vehicle. Is pretty long, and in short, we just call it PEMAC for ICV. This will be setting the restriction on both the enterprises and the production that produce L3 and L4 AD vehicles. Specifically for functional safety, the company should follow the complete procedures to develop the vehicles so that the functional safety risks can be completely solved, and the vehicles also have to be validated as per the requirements related to the functional safety. And in the SOTIF part is pretty much the same. They have to follow the basic procedures no matter to develop or validate the vehicles. Other than that, other institutions in globally, no matter in the States or other ISO working groups, they have like NISA 3.0. It's about the autonomous driving report, and also the UL 4600, and also the ISO technical report 4804. And these reports or standards are either talking about the relationship among functional safety, SOTIF, and cybersecurity, or about providing some kinds of approaches to help you conduct SOTIF analysis. So that is basically pretty much about the background and standards regarding SOTIF. So next, with this in mind, we can talk about more on practice and application of SOTIF, especially in China. So first is about the artificial intelligence and SOTIF. To human beings, no matter what kind of noise or layer you add on to the original picture, such as this panda on the left-hand side, in most cases, we are able to figure out that the right-hand side is still a panda. But for different types of algorithms, after a series of training, they are able to tell that on the left-hand side is a panda. But however, when you add another layer, especially like some noise, which might affect the color or the edge of the image, and as a result, you might see they might see the panda as a given. Although the AI algorithms can be, I would say, can be very powerful or smart, they may not be able to provide reliable results under certain kinds of scenarios, just like the previous speakers mentioned in the previous presentations. And so now we see the problem. And on the other hand, is this kind of algorithm widely applied in autonomous driving? And the answer is, unfortunately, it's yes. These algorithms are pretty key to the sensing system. For example, for like the computer vision algorithms, it's used to both classify the targets and also to provide the position and the speed of the target. So let's say if the camera is not working properly, then we might lose a part of the fusion data. That might be fine because we still have the radar and LiDAR working. But however, if we lost the target classification, then we may not be able to predict the movement of the target accurate. And finally, we are not able to create a path planning. Oops. Oh. Okay. Sorry. Can we go to the next page?
Do you have a problem to go to the next slide?
Yes, actually, yes. Yeah. Maybe I think there is a delay on my side. I'm not quite sure.
Okay. So
are we on the like?
This was the previous, and this is the
page
next.
5. Yes. Yeah, we got it. Okay, thank you. So this problem cannot be covered by nor cybersecurity, and actually SOTIF provides at least a concept to deal with this. This graph gives us a basic idea about how we can categorize all these scenarios. In this graph, we have 4 regions in total: hazardous, not hazardous, known and unknown. If we already have some risks detected, then the scenario fall into the area 2, which is actually the hazardous known scenario. Then there are some risk scenarios still cannot be detected at this moment. Then we put them into the area 3, which is the And ideally, we have different testing approaches for different types of scenario. For example, for Area 2, we can conduct simulation or proving ground test. But for Area 3, we can use the long-term road test in this manner. Yeah, and last part is about the engineering practice of SOTIF in China. This is more about our current project progress. So now we can talk about more regarding the general procedures of SOTIF. Basically, we can divide the whole process into the SOTIF development and SOTIF verification and validation. And we usually divide the problems into three parts. Into this four parts according to the function definition or requirements and the system architecture from the OEM. We provide some consulting service, includes item definition, error analysis of the insufficiency and trigger condition. And after that, we generate a scenario catalog for the OEMs or the tier ones so that they can use that for verification or validation. And based on this we call it a known hazard scenarios, we provide different verification approaches to the clients. And this testing approaches can include vehicle verification and hardware in loop or software in loop testing methods, etc. Yeah, so other than that, we actually divide the problem into three parts. So the perception is the first one and is the most important one, because most of the SOTIF related risks arise from the sensing system. We typically analyze the limitation of the three sensors, including camera, radar, and LiDAR. And due to its physical, technical limitation, the sensor performance can suffer a lot from the weather, road condition, or illumination. And this causes a lot of problems even when the vehicle is trying to driving inside the ODD. And next, we can move to the planning and control part. And this is the second part. And the problems occur here are mainly from the algorithm itself, as sometimes when edge cases or corner cases occur, the vehicle might not make the right decision even it senses the surrounding environment correctly. And last part is about actuating. The environment can physically interact with the vehicle through its it can be through its body and its tires, which can bring disturbance to the system itself. And with these factors, actually we call them trigger conditions, we can generate different scenarios that can be used for verification or validation. Especially in China, we have some unique scenarios, as you can see in this page, such as haze or like frequent construction site with workers and crossing the road in chaos, or like a traffic policeman standing on the post in the center of the in the center of the intersection. So those can be very problematic scenarios to our clients, and sometimes this cannot be solved easily, at least at this moment. But it's still worthwhile to figure out this situation so that we can identify the problems and let the vehicle to hand over the authority to the driver. And last part is about the functional modification or functional restriction. So actually, there we have like three basic approaches to modify the system. And so the first priority for us is to modify the system or improve the system so that the vehicle can work or drive properly in our ODD. For example, can add sensors or improve the accuracy of the sensors. That is the most straightforward one. But on the other hand, if we cannot improve the system more, then we can actually restrict the function ODD. So, for example, if we see a tow station or we see a construction site, and currently we don't have any solutions to these scenarios, then we can just we need to send a warning to the driver, then just quit the system, and then hand over the authority to the driver. So that is pretty much how we deal with the current problems regarding SOTIF in China. I think the time is almost there, and this is pretty much everything about my presentation. And let me know if you have any questions. And thank you, everyone. Thank you.
Thank you so much. So there is one question, and there are some more generic questions from the previous presentations. So then the specific question for you is, let me look. What are the chances that the autonomous vehicle ramps into the maximum weighted obstacle? This is a...
it can be pretty hard to really, I would say, quantify the chances. So let's just have a brief review about that scenario. So the problem is that the large white truck, it's laid down on the road, which can cause the problems to the radar. And also because the color is pretty much it's very similar to the surrounding environment, and so in this sense, this kind of obstacle it's creating problems to different sensors, and just so that is actually I would say the main problem of this scenario. So it doesn't really just only affect one kind of sensor. If one sensor is not working, we usually have other sensors working to avoid the accident. So the chances can be pretty low, considering this kind of scenario. So I would say it can be fatal, but the chances are can be quite low. Actually, yes.
Thank you again. So there was one question also related to learning, and whether autonomous vehicles learn all the time while driving or not. So this is a more generic question to all of the presenters, I would say. So whoever wants to jump in here and give an answer, or a few, would be okay.
I can volunteer to answer that question if you like.
Yes, please, Simon.
So there's we do differentiate in what we term sometimes online and offline learning. So if you have a machine learning function which is presented with different generations of data to optimize some type of fit-in function to its environment, for example, you show the function lots of different pedestrians which are classified according to their size and etc. And then we train the function, and that's been trained once. Offline training would mean we would train the function, maybe in a very iterative manner, and test the function and collect the safety evidence for the function before releasing the vehicle onto the road. And then at that point in time, the function is fixed and has the same functionality in every vehicle it's deployed in. Machine learning in general gives us the ability to continue to learn by adding more data. And there's different classes of algorithms that allow us to do this, such as reinforcement learning, which if we were to use those, it would mean that after deploying the functionality in the field, it could be that each vehicle learns differently and different behavior over time, which would make it even more difficult to have one safety argument for a whole fleet of vehicles. You would need to somehow continuously ensure that each vehicle, the way it's learning individually, would need to remain safe. Now that is yet another layer of safety hell, I guess you could say, right? And that is another layer of difficulty, which is why my prediction is we will not be generating safety standards to allow us to argue that type of online learning at least anytime soon, at least to allow for this online learning that could potentially impact the safety relevant behavior of the vehicle. So there's other reasons why we might want to do something like that, for example, to optimize the efficiency in the use of batteries for electrical vehicles, etc., by learning the behavior of the way the battery is being loaded and unloaded over time. But if we do apply that type of class of machine learning, it would be restricted in such a way that the changes in behavior will not be able to impact any safety requirements.
Very good. Thank you so much. So there are some, I saw there are some here and there, some questions related to what is the role of sensors. Can an autonomous vehicle see around the corner to identify pedestrians, for example? And also, what about communications and latency of communications? And in particular, also one question, the role of 5G, cellular network-based communication. So since we are very much beyond the schedule, so I would like to give very short answers before we conclude and come to the end and adjourn this session. Who wants to jump in? To give a short answer. The role of communication and sensors for safety.
If nobody else is going to, I'll offer it again. Yes. So, so I have some background here as well. But I think what we see is with the current set of sensors attached to the ego vehicle itself, there are limitations. These sensors can't see around the corner. They can't use common sense to make certain predictions about who could be hiding around the corner, or if there's a school around the corner, etc. The way the pedestrians may behave differently. The use of the infrastructure that is available either within an inner city or on highways, etc., is a potential bonus for safety, I see personally, and it could allow us to increase the level of performance in automated driving by making use of this data that is available, and therefore compensating for some of the weaknesses we have. However, if we do apply that type of technology, then we also need to make sure it's safe. So can we rely on the data that the infrastructure is providing us with? Do we know that the data is up to date and timely and hasn't been corrupted? And this is where obviously 5G networks have a set of intrinsic properties built into them to allow the data transmission to be somehow more trustworthy in terms of latency times and guaranteed bandwidth and those sort of things. This is, I think, going to be a big area for the future as well. The interesting thing here is it's not just down to the automotive industry. We have to have the city authorities involved, telecoms companies involved. It will require a much greater level of cross-industry collaboration, which is why standards will be absolutely key here.
Now, thank you again, Simon, for the lecture after the webinar.
No problem.
So with that, I wanted to remind you and at the same time to invite interested audience to participate and make contributions to this industry connection activity of IEEE. As already said at the beginning, it's an open platform. So participation is easy. Just email and you will be invited to meetings. You may bring up the questions not yet answered here today due to time constraints. And these open questions could also trigger the development of agendas for future webinars or even events, or hopefully also in-person workshops, perhaps, or conferences. I wanted to bring to your attention, so the industry connection, they have already planned a next webinar, and what we had in mind in the group is it's about artificial intelligence. So the working title for the time being is Mind the Gap, Trustworthy AI for Autonomous Vehicles. So it will take place on the 30th of June. And of course, you're all invited to participate, to attend again. And having said that, I wanted to thank you, to thank the presenters, and thank the audience for the interest and the interesting questions. And again, invite all of you, in case you want to discuss further, to email to either Axel Deike, who is the chairman of this group, or to the email address given here, AV for Mobility as a Service at IEEE.org. Thank you so much for being with us today, and have a great day. Thank you.
Thank you. Goodbye, everyone.
Thank you.